So good afternoon, everyone. Welcome to this NEASQC webinar, the fourth of a series of 9 between now and February 2022. I'm Pascal Bernier-Brunner. I'm the communication leader for the NEASQC project, and I will be your host today. This webinar is recorded, and you will receive the link to the recording in 2 days. It is in listen-only mode because we had a lot of people registered, but you can use the Zoom Q&A panel to ask questions to the speakers, and you will also see the questions asked by the others. You can upvote questions or comment on them, and the chat is also open to exchange with us, with the organizers, or with the other attendees. So, before I hand over to today's speakers, I would like to introduce the NEASQC research project and our use cases. I'll try to keep it short, I promise. So NEASQC stands for Next Applications of Quantum Computing. It's a 4-year project. It's funded by the European Commission's Horizon 2020 program. And we are a consortium of 12 companies and research labs. And the objective of the project is to boost practical applications of quantum computing in the NEASQC era. So we are a use case centric project. Every use case is committed to develop open source NEASQC programming libraries. And each use case is endorsed by an industrial partner and investigated by an integrated team of industrial and academic partners. And I'll briefly go over the use cases. So 9 of them, as I said. We have 2 use cases in chemistry, CO2 recapture and drug discovery. And if you have an interest in chemistry, we have a workshop at the EQTC conference next week about our chemistry use cases. And then the second domain is machine learning and optimization. That's where we are today. We have 4 use cases in this area: reinforcement learning for stock management, hard optimization problems for energy management, financial applications, and today's subject, HPC mesh segmentation. And then the third domain is symbolic AI and graph algorithmics with quantum natural language processing, quantum probabilistic safety assessment, and quantum rule-based systems for breast cancer detection. And the project as a whole is committed to build a community with potential users of industrial NEASQC applications, I mean, outside of the project. So that's why we are organizing this webinar, to share knowledge and to exchange with beyond the project partners. Sorry, I'm trying to move my slide. No, oh yeah. I'm not patient enough. I move 2 at a time. Okay, so let's get on with today's agenda. Sorry about this. First, I would like to introduce Dr. Vedran Dunjko from Leiden University, who will moderate the discussion today. He's the work package leader for machine learning and optimization use cases in our project. And he's more than just a moderator. He organized this webinar. He organized the previous 3 webinars we had in November. So he built this agenda. So Vedran, can you explain how you came up with this agenda?
Sure, Pascal. Thank you very much for the introduction. So basically, as you clearly explained, this project is all about bringing together specific real problems from the industry, which we call use cases, together with potential solutions that are going to be further developed and identified by academic partners. And in writing of this project, we came up with interesting use cases and the best methods that we could come up at the time, right, which was now something like 2 years ago. But of course, technology develops, and we have new ideas as to what quantum computers, especially near-term quantum computers, could be used for, and what things are probably not going to be the so-called proverbial killer apps, and we have to be moving ahead with the times. So in order to prevent this overfitting of problems and algorithms one to another, The idea behind this seminars was to invite an external expert who is roughly working in the area that we're interested in. In this case, it's in combinatorial optimization with quantum computers and near-term quantum computers, together with an expert from the industrial partner. And today, this is going to be Jeanne Pellerin talking to us, who is an expert in mesh segmentation. They will be presenting their own works, their own views on their distinct research and problem areas. And then in the discussion section, we will bring them together for the first time. So the main observation here is that we're not trying to tailor and very specifically align the progress in quantum computing with what we would like it to do, but rather try to identify new, perhaps previously unidentified connections, or maybe places where we expect things not to work. So with this, I would like to slowly move the attention to the most important person of the evening for us. And in this case, this is Martin Leib, who is our external expert. He's definitely one of the up and coming stars in quantum computing. And he has a very rich background stemming from actually quantum devices and quantum machines and quantum annealing. Then he moved to software development for quantum computers in various models of quantum computing, and he's connected to industry and has worked with Volkswagen Data Labs, and is now the team lead for quantum algorithms and applications at IQM. So I'm extremely happy to have him today with us. So Martin, with this, I will invite you to give us your presentation. You have something like 40 minutes. Towards the end, in the last few minutes, I will show up in your slides. So you know, when you see me, it means we're close to be wrapping up. Following that, we will have a few technical questions, and then we will move to our next speaker. So with this, please, the floor is yours.
Yeah, thank you for the nice introduction. Trying to show you my slides. Can you see my slides now?
Yep.
Yeah.
Perfect. Perfect. So again, yeah, thank you for the introduction, and thank you for this the invitation to this very interesting series of talks. So I'm going to give an introduction to quantum approximate optimization algorithm. My talk will be roughly divided into 3 parts. First, I want to set a little bit the stage. So what kind of problems are we looking at? And after that, I will be introducing into this quantum approximate optimization algorithm. And finally, I will go a little bit into depth on advanced topics of QAOA. And first of all, I want to make the usual disclaimer for things such as that. All the choice of work that I presented are inspired by my own work and by no means represent every work that has been done in the quantum algorithm, in this quantum approximate optimization area. And I will also shamelessly advertise my own work here. And so, okay, to start, so what kind of problems are we considering? So it's combinatorial optimization problems, and specifically NP hard optimization problems. And typically, so when we're talking about that, that could be a traveling salesman problem, for example, or a job shop scheduling problem. And the decision variants typically of these problems lie in the NP complete class, which means there are polynomial mappings between these problems, and all we have to do is tackle one of these problems, and insights that we get on one of these problems sometimes can be transferred to all the other combinatorial optimization problems. And the kind of paradigmatic example that we are using for QAOA is the spin glass, which is also an NP complete problem. So what is a spin glass problem? Let me just, okay. So it's basically a collection of binary variables. As a physicist, we tend to think of spins. So binary variables would be 0, 1, spins would be 1, -1. So systems that can be in 2 states. And we combine that, this set of binary variables, with rules involving pairs of these variables. And a rule is basically a way to ascribe an energy cost to the configuration of these two binary variables that are involved. And now a solution, we call a solution or a ground state, if you're a physicist, to the spin glass, an assignment of these binary variables such that the sum of these energy costs is minimized. So sum of this energy costs would be the sum over the rules that define these energy costs. What is very instructive and helps to understand a little bit what is happening is that the spin glass representations can actually be, or the spin glass can actually visualize as a graph. And so for every binary variable, you would introduce a node, and for every rule that connects pairs of these binary variables, you would have a edge connecting these two nodes. And this spin glass representation is kind of a assembler, a common language that we need to translate all of our problems to in order to enable a solution with either quantum annealing or, as I'm going to present now, QAOA. So, so what is this quantum approximate optimization algorithm? So the general idea is to use this Ritz variation method to find a low energy state of a quantum mechanical Hamiltonian, diagonal Hamiltonian that is a function of the loss function that we define for our combinatorial optimization problem. So how do we do that? So we map these binary variables that I was talking about before to Pauli set operators, and with that we map this classical function that describes the energy of our spin glass to a quantum mechanical Hamiltonian, which is diagonal. And now we set up a family of states, a parameterized family of states in the Hilbert space. And we try to find the representative within this family of states that minimizes the expectation value with respect to the problem Hamiltonian that is defined by the problem. And we are guaranteed by the Ritz variation in principle that this gives us an upper bound to the actual ground state of the problem if we fulfill this normalization condition on the variation state itself, which is basically given by the rules of quantum mechanics. Now, how do we choose the variation state? I mean, a general strategy could be to kind of come up with a family that is most expressive, because the basic assumption is that one of these states in the Hilbert space is your solution, and you're trying to get as close as possible. So you could say, okay, maybe let's search for in a family that almost entirely spreads through the Hilbert space. That brings a couple of problems with it, because typically then you're offloading the optimization problem to this classical part, optimizing the parameters. And there's also this kind of barren plateau problem where the gradient that you need for finding the optimal state within this parameter space actually vanishes. So we want actually in our variation state have as little parameters as possible. And that is possible if we search for a variational state that is inspired by the task. And to understand a little bit more how this guiding principle leads us to the QAOA state, I want to quickly make a detour and tell you a little bit about quantum annealing. So in quantum annealing, what we do is we prepare the ground state of a problem-independent mixer Hamiltonian. So this is typically a Hamiltonian that is just the sum of local Pauli X terms. And the ground state of that Hamiltonian is very simple, it's separable, and you can easily prepare that. And then you slowly transform the Hamiltonian that is governing the system from this initial problem-independent Hamiltonian to the problem Hamiltonian itself. And by virtue of the adiabatic theorem, if you're doing that slow enough, you are guaranteed to end up in the ground state of this problem Hamiltonian. Now, the kind of time dynamics this generates is defined by this time propagator, which is a very complicated thing. And it is known that you can actually approximate that with a kind of stroboscopic version of doing that. So instead of slowly switching from the initial Hamiltonian to the problem Hamiltonian, you apply the problem Hamiltonian for some time. Then you apply the mixer Hamiltonian, the problem Hamiltonian, and again, and according to their strength. And now QAOA is actually using this kind of stroboscopic version of quantum annealing and makes the length of these time intervals that we apply the mixing Hamiltonian and the problem Hamiltonian variation parameters itself. And this has the nice advantage that we know if we increase the number of these stroboscopic steps to infinity, we are approximating quantum annealing dynamics, and with that have this guarantee from the adiabatic theorem that we are finding the optimal state. Now, to go a little bit into more detail, so what does this mean? How do we set up this whole algorithm? So we have this parameterized circuit, and we initialize this parameterized circuit with some random parameters, these variation parameters, so the length of these stroboscopic steps. You could do this randomly. There are a couple of better ideas already, but for the sake of simplicity, just assume that it's random. Then you run this QAOA circuit and you measure that multiple times in the computational basis. And with these measurements, you actually approximate the expectation to the QAOA expectation value, so which is the expectation value of the problem Hamiltonian with respect to the QAOA variation state. And now you use some classical optimization routine, which is typically borrowed from classical machine learning, to update these parameters such that your QAOA expectation value decreases until some value that you're satisfied with. And the last step would be to output the best measurement result you got during that procedure. And that is kind of the solution to your problem. Now, what is actually, so this variation circuit, how does it look like? So what you do is you, for every binary variable in your spin glass problem, you introduce a qubit. And then you initialize the qubit register in a superposition of all computational basis states, which is the ground state of the mixer Hamiltonian. And the first thing you do is apply this problem Hamiltonian. And now this problem Hamiltonian is a sum over these energy terms. And the energy terms in the spin glass language are basically just these ZZ terms. And you can decompose that into two body ZZ gates with a angle, and this angle is the variation parameter. So what you do is a bunch of these two qubit gates, and if you do that, if you do all of them, you basically implemented the time dynamics that is generated by this problem Hamiltonian. After that, you apply the mixer Hamiltonian. And again, the mixer Hamiltonian is a sum over this local sigma x terms, and we do this for some variational parameter beta 1. So what that means in the circuit picture is that we do local rotations in a direction that is perpendicular to what we have done before. This is important, so not to make things very trivial that we're doing. And so what I've described so far, this is basically what I would call one block of QAOA, and you can actually repeat this block a couple of times, and the more blocks you have, the better the result should be, because if you have an additional block, you could have chosen these additional parameters to be 0, and you would have generated the quality of the result before. And with that, I would like to progress to a little bit of advanced topics of QAOA. And what is a very general notion within this QAOA area is this notion of a reverse causal cone. And if you consider a correlation function, which is defined for 2 qubits I and j with respect to the QAOA output state, you could think of that, of a pictorial representation of that a little bit, which would look like that. And so you have your, so this is actually the cat state, so it's QAOA state, and that would be the bra state here. And this mean value can be symbolized like that. And now it's instructive to think which of these gates that we are seeing is actually affecting the value of this correlation function. And you can identify a set of gates that directly affects that. So if I change anything in these gates, I will change the value of the correlation function. That, interestingly, is not the case for all the gates that are now still blue. So how can I see that? So this gate is actually commuting with that correlation function here. And here I have his unitary conjugate partner. So if I combine these two, they're basically just one and they disappear. So we can actually erase all these gates and still calculate the exact value of this correlation function. And as you can see here, this already gives me a little bit, I can save something in computational complexity because these 2 qubits here are not involved at all in the calculation. Which already brings me to fact 1 that is interesting about QAOA, that is actually under some circumstances, it's easier to calculate the QAOA expectation value, so the average performance of QAOA, than it is sampling from the QAOA state. So just the complexity of sampling from the QAOA state is actually exponential for even the level 1 QAOA version, because there is a paper by Fahy where they show that level 1 QAOA is equivalent to IQP circuits, which are themselves have this exponential computational complexity if you're trying to sample from that state. So, but with this kind of notion of this reverse causal cone, we can actually show that under some circumstances, the expectation value is easier to calculate. How do we do that? So if you see that expectation value and you still have in mind this notion of a spin glass, that there's a couple of rules and weights of these rules, you can actually decompose that QAOA expectation value into these correlation functions. And all these correlation functions have their reverse causal cones, and you're basically only calculating on the reverse causal cone. And another interesting way to look at that problem is if you think of this reverse causal cone in terms of the problem graph. So for example, if you're looking at a correlation function involving these 2 qubits and you have a level 1 QAOA circuit, in order to come up with the support of that reverse causal cone that is generated by this QAOA circuit, you have to include all the gates that directly are connected to this kind of correlation functions. To this kind of correlation function. And if you have a QAOA level 2 circuit, you would have to include additional gates that are connected to the already connected gates within the support of this reverse causal cone. And you can come up with different situations. So for example, if I have this correlation function, I need to include all these orange gates. And with that, I would also have to include all the qubits that are involved here. So I can basically throw this qubit away to calculate this specific correlation function. And with that, I go through all these correlation functions. And because it's a spin glass, I know that the number of correlation functions is polynomial in the size of the system. So the number of binary variables in the spin glass, and I can go through them fast and calculate only on the reverse causal cones. So what is the resulting computational complexity? So the prerequisite that this computational complexity is actually smaller than sampling is that I'm looking at a finite degree problem graph. So if for a finite degree means every node in this problem graph only has an upper bound on the number of neighbors it's connected to. With that, I make sure that this reverse causal cone doesn't grow through the entire QPU in just one step. And now what is the numeric complexity for that? You have the number of correlation functions that you need to calculate, and an upper bound on the number of qubits that can be connected to one correlation function. And that is an exponential of the number of layers in your QAOA circuit, but not an exponential in the number of in the number of parameters of this problem. And okay, and with that, we can actually already derive another fact about QAOA. And this is the fact that energies of measurement results from QAOA circuits concentrate near the mean. That means if you're sampling from a QAOA state that is in some, a QAOA circuit that is in some way shallow, you're very likely to get a measurement result whose energy is very near to the mean value. So how do we see that? So we can actually calculate the square of the variance of the mean value of this QAOA mean value. And you see we have here a quadratic term which ends up in a double sum over, again, these correlation functions. And you subtract from that this single sum of a single correlation function, again with this reverse causal cone, and square that. So that means, so there are two different cases. So either the reverse causal cones of these two correlation functions, the green and the red one, either they intersect or they don't intersect. If they do not intersect, that means that I can decompose that four body correlation function, so to say. So, and if that is possible, then there's always a partner in this sum that will just ideally cancel that term. So to come up with an upper bound on that, you actually have to count the number of times it happens that these two correlation functions have reverse causal cones that intersect. And that again is the number of the number of rules that you have in the spin glass, the number of edges that you have in the problem graph, times the number of qubits that are in the reverse causal cone of a QAOA circuit that has actually double the size. So this is 2 times P now. And interestingly, so what we've seen here is the square of the variance, actually. So that means the square of the variance is proportional to the number of edges in the problem graph. And it means that the variance itself is actually proportional to the square root of the number, while the mean value is proportional to the number of edges in the problem graph. And with that, we have basically shown if you make a measurement on a QAOA circuit, you're very likely to get a result that is very close to the mean value. Another thing that we can actually come up with is some lower bound on the performance of QAOA, which is of course always an interesting question. So what is the performance of QAOA? And also with the technique of reverse causal cones, you can actually calculate that. And that is a result actually extracted from the original Fahy paper. And it's the following. So that if you have a level 1 QAOA circuit and you're trying to tackle a max cut problem, which is basically a spin glass problem, but all the interactions are antiferromagnetic and of the same strength. And you're tackling that max cut problem on 3 regular graphs. And with that, you can actually show that there is some lower bound for the approximation ratio. So what is the approximation ratio? It's basically the QAOA mean value. And now we are trying to maximize that. And it's the QAOA mean value divided by the maximum cut that is possible. So max cut is a problem where you are given a graph and you have to partition the set of edges into 2 sets such that the number of edges that are connecting these 2 sets is maximal. And now you can again play this trick. I mean, so the problem Hamiltonian is a spin glass Hamiltonian. You can decompose that spin glass Hamiltonian into the correlation functions. And because it's a very simple graph, it's a 3 regular graph, and you only have a level 1 QAOA circuit, there's a finite number of possible supports for these reverse causal cones. And just to calculate this mean value, you just have to count the number of times these actually show up. And as it turns out, the most difficult to optimize subgraph is this tree graph. So to get a lower bound on performance, you can just assume that all of these subgraphs were the tree graph. That would mean that we have to take this times the number of edges in the graph. And what is an upper bound to the maximal cut is the number of edges. Yeah, you can never cut more than all the edges. And with that, we can actually show that the lower bound for the approximation ratio is given by the maximum of this correlation function with respect to the 2 variation in parameters we have for this level 1 QAOA circuit. In that case, it's 0.6924. Now, another interesting thing, which is actually an empiric effect, and I think it's an empiric effect, I haven't seen any proof yet, is that these optimal parameters actually concentrate. To understand that, we did a small experiment. So what you can see here is the following thing. So we created a random 3 regular graph of some specific size. So here it's size 6 up to size 18. And we defined a max cut problem on that problem graph, and we set up the QAOA circuit, we optimized the parameters, and we repeat that for a couple of times and make a histogram of these optimal parameters. And naively, you might have thought, okay, these are random problems, so I'm guessing the optimal parameters should also be random, and we would have gotten some equal distribution of optimal beta and gamma parameters. But that's actually not the case. So they concentrate at some specific value. And the interesting thing, this specific value is actually independent of the problem size. So we're going from 6 up to 18 nodes in these problem graphs, and we are averaging in the smaller cases over roughly 200 instances. Here we are averaging over 26. And these 2 things. So we can actually calculate the performance of QAOA classically easy. And this concentration of parameters now gives us an opportunity to get actually rid of this auto-optimization optimization loop. So we don't have to optimize these parameters. In some circumstances, we can just guess very good parameters. And how do we do that? So if you have a three regular random graph, that, as I already told you, there's only a finite number of possible subgraphs that you can have. And as it turns out, if you increase the size of that graph, then the only relevant, meaning the most probable subgraph that you will see is this tree graph. And now this tree graph enables another level of making the algorithm that calculates this specific correlation function more easier. And so how you would do that is with the tensor network technique. So we are trying to calculate this correlation function with tensor networks. So what we do for that is we have this QAOA circuit. We replace each and every gate with tensors. So a 2-qubit gate would be a rank 4 tensor, and a 1-qubit gate would be a rank 2 tensor. And the first thing is, what we do is we decompose these rank 4 tensors, which are the 2-qubit gates, so this phased ZZ rotation, into rank 3 tensors. And that actually enables us to contract all these 1-qubit gates into these rank 3 tensors. And that basically comes at no computational cost. It scales linearly with the number of qubits, but all these operations are fixed complexity rotation operations, do not depend on the size of the problem. And as a last step, we contract along the qubit lines. And what we end up with is a tensor network that is exactly given by the support of this reverse causal cone. And now an interesting fact comes into play, that the contraction complexity actually of a tensor network is proportional to the exponential of the tree width. The tree width is a graph theoretical property that tells you how far is this specific graph away from a tree graph. And that basically means if we have a tree graph, and we always have a tree graph because we found out that the most relevant subgraph in the n to infinity case is actually always the tree. Then you have basically a classically fast way to calculate the average performance in the infinite size limit. And we actually use this inside and calculate QAOA in the infinite size limit. And we optimize the parameters in the infinite size limit. And we use these parameters that we optimized in the infinite size limit for finite size problems. And this is basically what you can see here. So this is on the y-axis, you have the residual energy. So the lower, the better. And we are plotting against the number of levels in this QAOA scheme. And we're comparing our method, so this tree QAOA, to two, I'd call them vanilla QAOA methods, where we optimize each and every instance. And we compare that to actually two different classical optimizers, which is ADAM and BFGS. So it's just two classical optimizers. And what you can see, the performance is basically on par with this ADAM optimizer, better than the BFGS optimizer, and even outperforms this ADAM optimizer. And that is remarkable because we operate QAOA here completely without an optimization loop, an auto optimization loop. We just guess the good parameters and use them for every instance that we come across. And we actually outperform even ADAM QAOA because ADAM QAOA in this high dimensional optimization space was not able to find the global minimum. There's another interesting thing I want to talk about, and that is a connection between QAOA and optimal control. So you can actually think of quantum annealing and QAOA as one as specific cases of a general way to steer a quantum system. So think of the following situation: that you have a independent Hamiltonian and some control function S of t that tells you how much of the mixing Hamiltonian do I include and how much of the problem Hamiltonian do I include. And what you can see here is this control function as a function of time. In this picture, basically, the quantum annealing would be a slow ramp coming from initial Hamiltonian, problem independent Hamiltonian, going to the problem Hamiltonian, and QAOA would be this bang bang type stroboscopic thing. And now one can basically set this up as a quantum control problem. So you have a control, which is this function S of t, which is in between some boundaries, and you can do anything you want, but the task is to start from a problem independent starting state. So this is, in our case, that would be the equal superposition of all computational basis states, and come up with a solution that is minimal with respect to that. So this is the result is a functional of this control. And with that kind of rephrasing of QAOA, you unlock the toolbox of quantum control. And there is one thing which is called this Pontryagin principle, and it tells you if the system has this kind of property that your control is actually has some threshold, has some barriers, and it's linearly controlled. And in our case, that means that these controls enter linearly in the Hamiltonian. Then the optimal protocol that you can do is of this bang-bang type. So it's really the control function switches rapidly between the extreme cases that it can take on. And with that, they preliminary have shown that QAOA is strictly superior to quantum annealing. There's been a couple of publications in the meantime where they show actually one of the basic assumptions that they did, that this control Hamiltonian never vanishes, is actually not completely true. So apparently there is some mix between some annealing dynamics and QAOA dynamics that is optimal. And that's because they kind of overlooked that something can really vanish, and that's not unlikely. And the last thing I wanted to tell you a little bit about is introduce you to a QAOA experiment. So, and specifically, I will be talking about this experiment done on a Sycamore chip by the Google Quantum AI team. And there's basically two things they highlight for the experiment. And one is that they basically were able to solve problems that are non-hardware native, and I'm going to explain to you later what that means, up to a 90-bit size in non-hardware native problems. They showed some improvement over random guessing. So the hardware that they were using was, as I said, this Sycamore chip, and the hardware grid looks a little bit like that. And if you have a problem graph that exactly matches the hardware graph, you can actually implement this phase separator. So the transformation that this problem Hamiltonian will generate without any overhead. You can directly act with this ZZ gate. But if your problem graph is not commensurate with the hardware graph, then you have to implement swaps in order, because it could happen that two of the qubits need to have a ZZ gate that are not adjacent in the hardware graph. And you have to swap the information until they're next to each other. Then you can affect this gate, and only then. And there's a minimal overhead you have in depth with that, which is scaling as a square root of the system size. And for the Sherrington-Kirkpatrick model, which is basically an all-to-all connected problem, you can use the swap network as an embedding, and with that you have an overhead that is linear in the problem size. And what you can see here is the average performance of QAOA normalized to the optimal solution. So that means basically 0 is the result from the QPU is not discernible from random guessing, and 1 would be the perfect solution. And what they show here is the unitary simulation of this experiment, and you can see it's not reaching perfect the perfect solution, because it's just a level 1 QAOA circuit, and you get this degradation as a function of the system size. And here you can see the measurement results, and that is basically their main result is here, that they can show that for non-hardware native problems, they do have some results which are better than random guessing, even though they have to include these swap gates to actually make the problem graph fit the hardware graph. And another thing that they showed is that they can actually improve the approximation ratio as a function of the level of QAOA. So for the noiseless experiment, you can improve the quality if you improve the number of layers. But in a real experiment, you always have this trade-off of increased performance because you increased the number of layers, and you would have a better result if your QPU was completely unitary, but you have this noise. And because of that, you have this trade-off. And for the hardware native problems, they actually showed that they have some improvement for up to level 3 QAOA circuit. To make this a little bit more visual, they did this this histogram here of problems. So what you see here is that 50% of the instances had the best result at the level 3 QAOA circuit, and the others were basically distributed. And that was also the first demonstration of an improvement as the number of levels in this QAOA circuit. Yeah, and with that, I'm basically at the end and would await questions.
Thank you very much, Martin, for this very in-depth presentation covering everything in the world of quantum approximate optimization. We are now running a little bit behind schedule, so what would happen now normally is just a few minutes for technical questions, and then questions with a bit of a more broader scope would be left for the large discussion section that we have 20 minutes for at the end of the next talk. But maybe I will ask one question that I see here in the chat. I've noticed a question from Yash Patel that I will defer for later. From Martin, I have a question here. Sorry, from Mark. How does warm start initialization for QA relate to your discussion and setting up a good ansatz?
This warm starting, so in general, so this ansatz discussion that I did before is really related. So that would be starting coming up with a quantum circuit that is a perfect fit to the problem, but we don't have to do any classical work before that. So it's directly inspired by the problem, by the specific instance of the problem. So this warm starting would be another technique where you do a little bit of classical work already, and then you don't start in this superposition of all computational basis states, but you already rotate into some direction where you think you have a better start there.
Okay, thank you very much, Martin. So with this, I think we will end this part of the presentation. And at this point, it is my pleasure to introduce Jeanne Pellerin, who is TotalEnergies R&D project manager in computational geometry and meshing. So Martin was discussing how quantum computers can solve one type of problem on graphs, which has to do with finding optimal cuts and optimal bipartitions in terms of cuts, which is an NP-hard problem. And now Jeanne is going to be talking about something else which has to do with graphs, but might be completely different or very related. And we're all very excited to find out. So with this, Jeanne, please, the floor is yours. for the next 15 to 20 minutes. And again, I will show up towards the end when we have a few more minutes left, so you know that time is.
I'll try to. Yeah. Thank you, Vedran. I'll try to share the right screen. I'm not completely used to Zoom. No, I cannot see. Okay, I'm not using Zoom, so I have to authorize. Or do you have to? I have to. I did not try this before. Sorry. I'm going to talk about mesh generation, which has been my topic for a few years now. Zoom is not allowed to access my slides, so yes. Okay, I have to set up my system preferences and okay. It does not. Oh, sorry. Do you have the slide? I'm sorry about it. Maybe this would. That's a bit.
Pascal, do you by any chance have slides on hand?
I'm not sure I have the latest version.
They're not changed. I'm sorry. I'm trying to.
That's okay. That's okay. Getting Zoom to work it's a complexity class of its own. Much worse than NP Hard.
No, and do not use it on. I have to. Okay, maybe. Okay. Should have checked this before. I have to disconnect. I'll be back in.
Okay, maybe we can take a few questions while.
Right, Martin. So, Yash,
do you see the questions in the Q&A panel? We have 3.
I see them. Yeah.
I will just read out the first question of Yash so that everybody hears them. So the question is, can one leverage the analytical results from the infinite size QAOA that you've derived and employ them to predict the parameters at a particular P level classically efficiently?
Yeah. I mean, that's exactly what we do. So we're looking at the infinite size problem for a particular P, and we're using these parameters for finite size problems. And okay, the next question is a more generic question. What do you think about extending the abstraction results of QAOA to more general VQE, QML type algorithms? So what kind of abstraction results are you thinking of? So you're talking about this Koenig paper?
So I'm sorry to interrupt this, but
I cannot ask questions.
I'm back.
I can ask questions, but I cannot reply.
Yash will give more input, I'm sure.
Yeah, Yash, please give more input in the chat or in the Q&A. So in the meantime, Jeanne is back.
Yes, I'm back. I'm trying to not get out. Zoom is like, do you see the full screen or just?
No, we see your presenter screen.
Yeah, my presenter vision. That's not what I.
Yeah.
Let's try to share the slides. This should be good. I'm sorry about this.
Now it's good.
Yeah, okay.
Now we're good. Thank you.
Yeah, so I'll talk about mesh generation, which is going to be a bit exotic compared to quantum computing. I don't know anything about quantum computing. I never used it. Maybe it may be of use because you'll see there are graphs there, and really like there might be some connected problems. So I'll present basically my contribution to mesh generation. I defended my habilitation like recently, and most of the slides come from there. So I'll go back to what is a mesh. Because you might not know what it is. So it's geometrical object, and basically we define it for a shape. So here it's a circle, it's a simple one. We're gonna set some points on this, and we're gonna connect the points with segments. And the rule is that the segments cannot intersect one another, and these segments are an approximation of the circle. And then if we connect the points inside, then we have triangles, and this is a 2D mesh of the interior of the circle. So from my point of view now, mesh is a polygonal puzzle or polyhedral in 3D. We're mostly interested into 2D and 3D meshes, and you have to follow 2 basic rules. there is no intersection between segments, triangles, or polygons, and the union of all the pieces matches the input shapes. So the idea is that there are two main components there. There is a geometrical component where you give the geometry of the points, and there is a huge combinatorial component in mesh generation. And the two of them are interdependent, and this is where the challenges arise. So why are we interested in general in mesh generation? The first one is not my main focus. There is like in computer graphics, you're representing everything with meshes, like behind the castle, the nice pictures in video games, in animation movie. There are meshes to define the geometry of everything. And in engineering at TotalEnergies, we're interested in mesh generation for a numerical simulation of physical processes. So mechanical processes, thermal processes, flow simulations. And we start here is an example of a pumpkin crash in Abacus. So this is pictured by Dassault. So you start from the physical model that is here quite simple. You have to discretize the geometry. So the geometry there, you have a flat surface, which is the surface, her surface, and you have the pumpkin that is represented there. You can see the small triangles. So this is the blue shape in the middle. And on the right, you can see the simulation results. So mesh generation objective, it really is there for us engineers. And it's the key part, from my point of view, of the simulation. If you do not have any mesh, you do not have a simulation most of the time. We're not completely interested in pumpkins at TotalEnergies. We're more interested in a really large number of simulations. Here are two examples. For example, we're interested in how can we model solar panels soiling. So you're in the desert, there are particles of sand, they're gonna end up on your solar panels and you will have to predict when you're going to clean them. And another example is injection of CO2 in the subsurface to store it. And there you can see the triangles there. So all this, the shapes, the geometry of the models is a mesh. I'm just here giving like the big objectives in mesh generation today, because it's a quite mature topic. It has been like, people have been working on this topic for decades now. And today we still have major challenges that are related to decreasing the time to build some kind of meshes. Depending on the elements you're considering, geometrical elements, it can be done by hand. So some meshes, the ones constituted of little cubes, I'm going to say they're hexahedron. They're on the bottom right. There are cubes or cuboids. And to generate meshes composed of 100% of this small cubes is mostly done by hand, by experts. And we do not have an algorithm to do it. And we also are processing bigger and bigger models, and we're generating hundreds of millions of little elements, so polyhedra for meshes. So time management is a key. And we're trying to get the best quality, so basically the shape of these geometrical elements to match requirements for running the simulation. So these are the big objectives today for mesh generation research. And in this talk, I will be talking about different types of meshes. So I'll be talking about one challenge for tetrahedral mesh generation. So these are the meshes constituted of tetrahedra. So the little pyramid with a triangular base that is in the middle. And I'll talk then about hexahedral dominant meshing. As I said, hexahedral meshing is really difficult. So people were trying to avoid and just to mix hexahedron and tetrahedra. And this will lead me to what I call theoretical meshing or combinatorial meshing, where I'll show some results about the combinatorics of meshes and why do we have problems actually with our algorithms today. So let's start with the easiest mesh generation. It's tetrahedral meshing. That's basically a solved problem. We use extensively the Delaunay triangulation and Voronoi diagrams, geometrical objects. I don't know if you might know them. If you have one set of points in general positions, so not degeneracy, then you match one set of triangle, the Delaunay triangle, and one set of polygons or polyhedra. So if you are able to build this Delaunay triangulation, you're able to generate a tetrahedral mesh, more or less. So the challenge is to do it really fast. So here is an illustration of the Delaunay triangulation algorithm that is the classical one implemented by almost all software. It's an incremental algorithm where you're going to insert all the points. There might be billions, and you're going to insert them one by one, actually. And at the step k plus 1, so I'm going to insert the pk plus 1 point. You have to locate it in the previously computed mesh. Then you're going to dig a cavity, so remove the orange triangles that are there. They do not fulfill a given criteria, and reconnect the point pk plus 1 to the existing tetrahedra there. So these 3 steps are repeated over and over, and this is an essentially sequential algorithm. And the key to efficient parallelization was to use some space partitioning. So this is a PhD student I supervised who did this, and he obtained really good results by using the subdivision curve that the computation and some optimizations are based on. So tetrahedral meshing parallelization is still today a problem that is not solved. Here it's shared memory, so we're talking there classical computers, and for distributed memory it's still really open, and we still are like, the target there is generating billions of tetrahedra. So what do we do, and how do we do that efficiently? So this is for tetrahedral mesh generation. I'll now switch to what do we do if we want to have hexahedra and combinatorics are arising. So as I said, there is in general no algorithm to generate hexahedral meshes. So hexahedral meshes constituted of 100% small cubes that are going to be deformed a little bit. So one idea was, okay, we can generate tetrahedral meshes. So the one in red on the right here, and we can try to combine tetrahedra into hexahedra, because if you take 5 or 6 tetrahedra, I'll show a picture on the next slide, you can glue them together and you get an hexahedra. So let's try to do that. Compute some graphs. Actually, it's based on some methods, use the graph approach to formalize it. But then the question that arose there when I implemented this was, okay, how many different subdivisions do we have? And there we're going to switch to theory. The question that appeared when doing this combination was, okay, we're combining tetrahedra, so this little triangular thing into cubes, and how many subdivisions are there actually? And it appeared that for the cube, it has been proven that there are 6 subdivisions into 5 or 6 tetrahedra. But for the cubes, like the hexahedra we're doing numerical simulation with them, and they're not exactly cube. The faces are not planar, they're bilinear, and they might look like this. And the question I tackled is, how many subdivisions are there? And this is where you have to to prove it, and to really explore all possibilities. We went to the enumeration of all the possible graphs connecting this, and used results of combinatorial geometry, of triangulation of the three sphere. So we were able to prove that there are 174 different meshes of this hexahedron. So this is where we enumerate all combinatorial possibilities. So this is the combinatorics part for the mesh, and we then have to prove if there are or not they can be realized in the 3D Euclidean dimensional space. And there we used some computational geometry ideas, and you are able to prove that only 3 of them, for 3 of these configurations, you will not be able to find 3D coordinates that will make this mesh valid. So this was the first step of this combinatorial exploration of meshes. It's not that's a real theoretical result that is not completely useful in practice, but we went further with hexahedral meshes, for which the combinatorial problem is really, I think, the key of all our problems. So here we switch a little bit. We are looking at meshes constituted of little cubes, and we want to fit meshes constituted of little cubes into different kind of boundaries. So the input is the quadrilateral mesh. So on the left are 2 examples of boundaries of quads given by Schneiders in 1996. And he presented them saying, okay, for these shapes, we do not know any any hexahedral mesh inside that matches exactly the boundary facets there. So this was a big problem for many years, and we proposed a solution to this. And there is the smallest hexahedral mesh in this pyramid on the left is 40 hexahedron. If you want, if you have like right intersections and follow the strict definition of the mesh. And on the right is another example. So this is a more recent result with from a paper by Ericsson 2014. And in this paper, it said, okay, for these 2 shapes, it's really easy by hand to generate a hexahedral mesh inside, but nobody managed to do it. So this was just a saying. And the question is, how do we mesh this quadrilateral boundaries? So the idea was first, okay, let's try to enumerate all the different possibilities. Starting from the quadrilateral mesh, let's try to insert vertices inside and hexahedron to generate all possibilities. Of course, that has an exponential cost. You have to deal with all the possible symmetries and filter out all the configurations that you have already encountered. And you can prove some minimal bounds for filling the shape, but it's not completely practical. On the right is an example of the 3 algorithms that result from this. So you start from the X boundary, you're gonna select 2 edges, so the 2 red edges, and you build a quadrilateral. So for a side, the gray one on the, you have 2 possibilities, either the one on the left or the one on the right, and then you go on like that, trying to feel the shape, and you backtrack when you are in a dead end. The 2 in the middles are not going to succeed. So this is really, it costs a lot, but we can get from that some operations, combinatorial operations, to reduce the number of hexahedra. So change the graph matching our criteria. And The solution that was proposed is another one where we explore a little bit a smaller space of hexahedral meshes. And the idea there is illustrated on the right. So you're going to try to build hexahedra going from the boundary to the inside of the shape, and you're going to build them in an order that corresponds to operations on quadrilateral meshes. So you're trying to build all the hexahedra until you match a cube, so you're finished, or a pre-computed hexahedral mesh, and at the end you get the result. So this is also extremely, this has also a really high cost of computation, but this is a practical algorithm that has been implemented and gives some hexahedral meshes for all possible quadrangulations, so all the combinatorial possible different triangulation of a sphere, so boundary. So this is a combinatorial result, and that matches criteria to have a valid hexahedral mesh. And we also got a really nice theoretical result on the number of hexahedra that are needed to mesh a given boundary. The previous boundary was about 3,000 times the number of quads, and we get it down at 78 the number of quads. So that's good step towards some more understanding of the theoretical problems behind hexahedral meshing. So under constraints, the constraints are strong, and hopefully we might get to some practical meshes, to some practical mesh algorithm at some point. So if I summarize what I said in this talk, is that there are software available today to generate meshes and run numerical simulation. If you want to generate hexahedral meshes, you might have to do it by hand. This is still a work in progress, and a lot of people are working on this. For tetrahedral mesh generation, it's more or less a solved problem. The challenges are managing the parallelization of the algorithm. And I presented there some theoretical challenges that are linked to computational geometry and graph problems for the understanding of the pitfalls of mesh generation. And I hope that if we can solve this theoretical questions really fast, maybe with quantum computing, I have no idea, we might be able to generate meshes for really complex configuration in the future. And that's the end of my talk. Thank you for your attention.
Thank you very much, Jeanne, for this fascinating introduction to meshing problems and the type of work you've been doing for the last few years. So this now brings us to our question and answer session, which would roughly have like 3 parts. So the first thing, I would invite any particular question specifically to Jeanne, maybe more technical with respect to meshing problems. And after that, we will try to do 2 things. One is sort of foster and inspire a bit of interaction between our 2 expert speakers, between Martin and Jeanne. Maybe you've seen things that you find interesting that you might want to clarify and come up with new ideas. And we will, of course, take further questions from the audience about whatever might possibly interest them. So I'm now opening the floor if anybody has particular questions, technical or otherwise, specifically for the problems of meshing for Jeanne. And maybe to open up the question, it's also hopefully going to help this discussion later on. Jeanne, just the basic question that I didn't immediately hear is, what is the input to the problem that you generate a mesh from? Is it a point cloud or what is it?
The input is a definition of the geometry of the shape you want to mesh. It might be a CAD surface, so it might, or some set of functions, but in general, it's already a mesh most of the time.
So it's a mesh, just not the kind you'd like.
Yes, it might be the mesh of this, like the problems are presented, it's the mesh of the surface and you want to mesh the interior.
I see.
You have a mesh of the surface, you want to mesh the volume, or you have a mesh of the surface, you want a better mesh of the surface. or you have a CAD representation, so B-splines representation of a surface, and you want to generate triangles or quadrilaterals.
I see. And maybe as a follow-up question, and I'm sorry for hijacking you 100%. Just in the problems that you discussed towards the end, which had to do with hex meshing,
Yes.
the computational geometry aspects. So you mentioned exponential time algorithms, right?
Yeah.
Exponential in what parameter of the problem? And do you by any chance have any results of complexity theoretical hardness? Like, are these things NP or are they above?
They are NP, I guess. I wouldn't like to say something wrong. There might be something written in the paper that was done by PhD students. I guess this problem are NP, and you just like trying to, it's exponential in terms of number of hexahedra are inside the, I might be wrong on this.
Because that would then mean that the more hexahedra you have, the easier, the harder the problem becomes. But is that really the case?
Yes. The more hexahedra you have inside, the harder it is to explore all the possible combinations, all the possible combination of hexahedra.
And a possible solution, then you can easily verify, but it's really the specification of the locations of the hexahedra and their actual local geometry. So you really have to specify each.
It's just the constraints. We do not deal with the geometry. We cannot. Mm-hmm. We have to deal with the combinatorial part, because the hexahedra difficulty is that it's really constrained. Each face of the hexahedra must have 2 hexahedra as a neighbor, and that's mostly the biggest constraint. And so you have like, it's really a rigid structure, and you're trying to fit some, like the top of a pyramid, you have 4 faces sharing 1 point, and you can see that in a cube, it's always 3 faces sharing 1 corner of the cube. So you're getting into trouble with this.
Okay, it's a fascinating set of problems. And I think at this point, I would like to move to the possibility of thinking about quantum approaches for any of these problems. And Martin, I absolutely don't want to put you in the hot seat, right? But this is a really a new set of problems that maybe we have not seen in the quantum world very much. But do you have any thoughts on where quantum computers could possibly play a role? Or maybe some questions for Jeanne, maybe research questions for Jeanne, which would help us inspire, devise new quantum algorithms in this direction?
I have a kind of general question. So this hexahedral mesh, so why are you aiming for that? Do you know that this hexahedral mesh could simplify simulation then?
Yeah, that's a really good question. I did not say this. For some simulation, for example, hyperelastic materials, there is no way around hexahedral meshes, or for some simulation they require they require hexahedral meshes, and everybody is ready to spend days building this. So for spectral elements, for some numerical schemes, they're required, and it's more efficient too when you have a hexahedral mesh compared to a tetrahedral mesh, depending on the applications and a lot of things. But yes, you're right.
Mm-hmm. Yeah, in general, it was a little difficult to get some, connections. But so one thing I was where you told a little bit about this parallel tetrahedral problem. So yes, where you have these walkers and they walk through the mesh, and
that's
kind of altering the mesh, and is the goal that they do not intersect each other?
Yes, if you do it, and the trick, like if you do it in parallel, the really difficult part is that they do not interact with one another, and that happens a lot, and it has been quite a tricky algorithm to parallelize because of this. It happens all the time at some point.
Mm-hmm. because that sounds a little bit like a problem we were looking at for a small period of time, but with no specific result there at VW. There was the problem of garbage disposal. So you have these garbage disposal trucks, and they're driving through a city, and they need to visit every flat in the city or every house in that city. And the question there was on how to optimize the routes of them, which would kind of strikes me at something similar, yeah, because they also do not, I mean, it doesn't make sense that they are on the same house.
Yes. I don't know. I think I would say this is an apparent, like, colleagues of mine are working on that operational research problem. This type of problem. This is still, this is quite far. There are some fun. I was thinking, like, there are some graph problems. We have some all these meshes. They might be seen as graphs. Actually, they're just graphs. Just like you can formalize them in different ways depending on where do you put the nodes and edges of the graphs, but they are more or less graphs.
If I interject, I mean, but the thing is, the difference I think between what we typically encounter is that your graphs are embedded in real space, right?
Yes.
They have XYZ coordinates.
Yes.
It matters, right? It matters. It kind of looks up for a particular way. So I'm trying to even imagine. I mean, so this is sort of this naive thing that one would try to do, is to somehow encode a particular type of segmentation into something which has an energetic cost, right? Which in fact, I mean, I suppose nature kind of does it, right? When it builds crystals and things like that, it's not a completely crazy thing to think about it. And I'm wondering if there's something solid, condensed metaphysics here that Martin could pull out of his physics days that kind of maybe corresponds to something like this. It's maybe not an obvious quantum algorithm, but something in that direction. So how to encode this such that we can actually evaluate energies, right? So assign, you need to encode the problem, right? The solution has to be encoded into quantum state, right? And then the cost should somehow be something which we can measure about the state. And then we're in business with our standard techniques. How would one do something like that?
I mean, but the cost in the end would be the quality of the numerical simulation that based on this mesh.
The quality is a problem, but you can also measure the quality of meshes before the simulation.
Like what constitutes a really good mesh? Right? What constitutes a really good meshing? Like for instance, it has to be a solid object. Like, so you have some hard constraints, right? You don't want things to be broken up and so on.
It's a trick. Yes, it depends, but you have some hard constraints, and you might, for it, like if you're dealing with a nice problem, you might aim for almost equilateral triangles like everywhere, and then you're gonna aim for some size variations that matches some input size variation that you want. And of course, then they cannot be all equilateral, and you're trying to optimize for this before the simulation. But still, mesh generation people do not know how to optimize all the time. So the cost function is not always well defined.
Right. That sounds like an extremely hard problem, right? It's like a knapsack with geometry, and you're only allowed to assemble it in a particular way, right? Sounds like a difficult thing. But at least the moment you mentioned exponential time algorithms, it always feels like we should have some way of doing something in a different way, not necessarily a better one.
Maybe if we get into the theoretical way of exploring this is my point of view. I might be the only one thinking this we should look at, because we do have problems that we do not know how to optimize things. But with this kind of approach, we're still far from practical algorithm that might be used by engineers, but maybe one, I don't know. This is far reach.
Okay, very good. So now I'm gonna quickly take a look at the questions in Q&A, and I see quite a few questions from Yash about QA. So Yash, I know works in QA as well. So maybe let me select one or two in time. So Yash had a question about extending the abstraction results of QA for a maximum independent set, max cut, and so in a k-diluted spin glass, and he clarifies that what he meant. The results of Bravi et al. On max cut, that whenever the level of the depth of the circuit is below logarithmic, then there are infinitely many irregular graphs that cannot be the Guman-Williamson relaxation bound. Do you think that this thing is going to carry over or can be carried over for a more general type of variation algorithms?
So sorry, I had to do a very Corona thing. I need to change because my kids are up there. But okay, so I think I know. So this is this Bravi-König paper where they do this recursive QAOA ansatz, and there are some extensions known to other problems. So the authors themselves extended that to a K-colorability problem. And but I'm not aware, but I mean, the general structure of this recursive QAOA you can actually adapt to any kind of variational circuit. So just to clarify for the others, I think the kind of application that Yash Patel is talking about is this proposal for recursive QAOA, which is a variant where you do not directly read out the samples, but you calculate all the correlation functions and you contract the strongest correlation function. So you just reduce the size of the system by 1, and you do this recursively. And as this is a technique that is just after the measurement, I don't see a problem extending that to also VQE or QML type algorithms.
Okay, very good.
I hope that answers the question.
We have one question from Jiu G. I'm hoping I'm not totally murdering the person's name. So they ask, how do you compare the practical applicability of different approaches, be it annealing or QAOA, in terms of size for the problems you can actually solve currently?
Oh, okay, so this is mainly a hardware question. Currently, because this quantum annealing is very close to what the hardware actually does, we can solve much bigger problems with quantum annealing that we can currently solve with QAOA. But it's unclear if quantum annealing will ever have some quantum speed up. So there is a proof that unitary quantum annealing has this quantum speed up, a polynomial speed up, but it's not known if there's any way to protect a real quantum annealer, a real noisy quantum annealer from this noise, as far as I know.
So we are now unfortunately close to running out of time, and I would like to circle back to the question of quantum computers and meshing a little bit, now that we had a second of breathing room in between quite intensive thinking there. So I wanted to maybe ask Jeanne, instead of trying to understand necessarily the problem, sometimes a good way is to try to understand the classical solutions, right? So in your meshing domain, can you tell us anything about the types of algorithms that sort of play a critical role? Like, for instance, do you ever end up doing sort of mixed integer optimization solvers or annealing or evolutionary algorithms? Because maybe understanding these could also help us understand where quantum computers could help.
Yeah,
Maybe as an intermediary step.
Yes, the algorithm that I've shown, like the Delaunay triangulation, like the key for tetrahedral mesh generation, the key is really this Delaunay triangulation construction algorithms. There are two, like there are different solutions in 2D or 3D, but the key is this, and this is like this is related to the also to the convex hull problems and everything like this. But this is really one key algorithm. And then what is really the way forward when you're trying to optimize a mesh or to do anything, you are always ending up doing some local optimizations. So you're gonna take a small sub part of the mesh and locally modify these cells to match the global function. I don't know if that's answering your question.
I think it might, specifically, it would be a very interesting starting point for even research questions. If you were to tell me that if you can handle larger local regions, then it's better, right? If it's not simply the case that a constant size local region is already enough.
Yes. Yeah, if you can handle larger size cluster of cells, I would say you might get out of some local optima in which you are stuck in 3D mesh generation, for example, for some problems. Yes.
This to me sounds like this very interesting dual thing where my gut feeling tells me that these mesh segmentation problems, that they could be sort of solutions to make use sort of smaller quantum computers, right? Where we also want to segment a large problem to smaller problems to be able to apply quantum computers. Well, now at the same time, we're somewhere in parallel thinking about, okay, we want to run quantum computers on something which is natively run in really, really large instances like you guys do. It feels like a very related thing.
It is related. I would say it's close to a graph partitioning problem.
Right.
We used it like a lot, and we used classical solution like Metis or Parmetis, or like to just partition the mesh as a graph. Okay.
I see Pascal has shown up. That means that we're close to having to end this conversation. Maybe I would like to ask Martin, I don't know if you want to conclude something like, have we as the quantum computing community been now issued the challenge to come up with good ways to help our mesh segmentation friends as a research line? Do you think that's something that would be worthwhile trying out?
Yeah, it looks interesting. So I'm especially connections to graph theory might be worthwhile looking at. But I do not understand enough to give a final statement, of course. But it looks very interesting. And okay. One comment, because there's a couple of very interesting questions from Yash Patel still standing. So if you want, just contact me via my email address. You can find that, and that's interesting question. I haven't thought about that yet.
Thank you, Yash, for all the active questions, but we have to talk about other things as well. So with this, I would like to thank Jeanne, Martin. Thank you very much for your contributions and for this very exploratory discussion. This is the kind of thing we're after, like new questions and new ideas. And with this, I would sign off and hand the torch over to Pascal.
Thank you. Well, thank you to our attendees for staying with us until the end. And thank you, Jeanne. Thank you, Martin, for your talk today and for answering all the questions we had. And but thank you to Vedran, because Vedran, this is our 4th webinar together. You've been a wonderful moderator. So, so thank you very much. And to everybody, well, we hope you will attend our workshop at the EQTC conference, or if you have no interest in quantum chemistry, just drop by in the in our booth. We have a virtual booth at EQTC. So if you have questions, I'll be there, and I can forward your questions to whoever can answer them. So thanks again to everybody, and bye-bye. The NEASQC webinars continue, so we hope to see you in our next webinars. Thank you.
Thank you. Bye.